The summer sky over northern Norway hung pale and empty on the morning of July 18, 1944. At Bodø airfield, German ground crews moved through their routines under the endless Arctic daylight, tracking Royal Navy carrier strikes against the battleship Tirpitz hiding in nearby fjords. Then someone spotted it, a bent-winged fighter sitting in a field near Sorvag, roughly 10 kilometers south, its inverted gull wings unmistakable even from a distance. Not wreckage, an intact aircraft. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Within the hour, Wehrmacht soldiers had secured the perimeter around the downed fighter, while Luftwaffe technical officers drove out from Bodø to inspect what they'd found. The aircraft was a Vought F4U Corsair, serial number JT404, from the Royal Navy's 1841 Squadron operating off HMS Formidable. The pilot, Lieutenant Matholi, had been forced down during an anti-submarine patrol and was already in custody. But the fighter itself sat undamaged in the field, engine cold, fuel tanks dry, waiting. For nearly 2 years, Luftwaffe pilots operating over Norway had been filing reports about these American fighters flying from British carriers. Fast, heavily armed, able to absorb punishment that would destroy a Messerschmitt. But intelligence assessments based on distant observations and combat reports could only tell you so much. Here, finally, was the actual machine, the fighter that was reshaping naval air warfare in both the Atlantic and Pacific theatres, just sitting in Norwegian grass, available for examination. The recovery operation began immediately. German engineers attempted to get Lieutenant Matholi to explain the wing-folding mechanism so they could transport the fighter more easily, but the British pilot refused. It didn't matter. By evening, the Corsair had been loaded onto a barge and was being ferried south toward Narvik for preliminary inspection. Every technical officer in Norway understood what this capture meant. This wasn't just another downed enemy aircraft. This was a window into American aviation engineering, a chance to understand exactly what the Luftwaffe was facing as Allied carrier operations intensified. By early August, the Corsair had been transported to Germany itself, arriving at Erprobungsstelle Rechlin, the Luftwaffe's central military aviation test facility near Laz. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Rechlin was Germany's equivalent of the Royal Aircraft Establishment at Farnborough, the proving ground where every Luftwaffe aircraft type was evaluated and where captured Allied fighters were dissected to understand their capabilities. By 1944, Rechlin's engineers had examined Spitfires, Hurricanes, P-38 Lightnings, P-51 Mustangs, and B-17 bombers, but they'd never seen an F4U Corsair. The fighter arrived at Rechlin in pieces, partially disassembled for transport, and was immediately assigned to the captured aircraft section. Technical officers catalogued every component: serial numbers, construction techniques, materials specifications. The initial documentation noted that the aircraft was listed as under repair, suggesting the Germans intended to make it flyable for comparative flight testing. That process would take weeks, possibly months, given the specialized parts and tooling required for American aircraft systems. While mechanics worked to restore the Corsair to flying condition, engineers began the detailed technical examination that would define their understanding of American fighter design philosophy. What they discovered during those first inspections would fundamentally challenge their assumptions about what made an effective combat aircraft and reveal engineering solutions that German industry, by mid-1944, simply couldn't replicate. In 1944, German fighter development was reaching a critical crossroads. The Messerschmitt Bf 109, which had dominated European skies from Spain through the Battle of Britain, was being pushed to its absolute limits. The G-model 109 seconds now entering service could reach over 400 miles per hour at altitude and carried heavier armament than early versions, but the basic airframe dated to 1935. Nearly a decade of incremental improvements had stretched the design as far as it could go. The Focke-Wulf FTW 190, introduced in 1941, had provided the Luftwaffe with a formidable alternative. It was fast, heavily armed, and could absorb more battle damage than the lighter Messerschmitt. But by 1944, Allied fighters had evolved to match or exceed its capabilities. The latest Spitfire Marks could outclimb it at altitude. American P-51 Mustangs could outrange it by hundreds of miles. And increasingly, Luftwaffe pilots were reporting new American fighters appearing over European skies that combined speed, firepower, and durability in ways that German aircraft couldn't match. The intelligence gap facing German aviation was becoming acute. Pilot reports from the Eastern Front, the Mediterranean, and increasingly from defensive operations over the Reich itself, described American fighters with extraordinary performance characteristics, aircraft that could dive away from pursuing Messerschmitts at speeds that made interception impossible. Machines that absorbed 20mm cannon hits and kept flying. Fighters that carried enough ammunition for sustained combat and enough fuel to escort bombers deep into German territory. But pilot testimony from the chaos of combat couldn't provide engineering data. Combat reports couldn't tell you wing loading figures, structural design specifications, engine management systems, or manufacturing techniques. They couldn't explain how American engineers had solved technical problems that still limited German aircraft development. The Corsair sitting in the Rechlin hangar represented something German engineers desperately needed. Not estimates or observations filtered through combat stress, but hard data from an actual American fighter they could measure, weigh, test, and analyze in detail. There was also a psychological dimension to the capture that went beyond pure technical intelligence. German aviation had been built on certain fundamental assumptions about fighter design. That performance came from lightweight construction and aerodynamic refinement. That skilled pilots didn't need heavy armor or redundant systems. That elegance in design reflected superiority in engineering. The Messerschmitt philosophy had always prioritized speed and climb rate through weight reduction. Even the Focke-Wulf, though more robust, sacrificed some performance for its additional armament and protection. The Corsair represented a completely different answer to the question of what made an effective fighter aircraft. And as German engineers began their examination at Rechlin in August 1944, they started to understand just how different that answer was. The external inspection revealed an aircraft that looked almost brutish compared to German fighters. Where the Bf-109 was sleek and compact, the Corsair was massive. Where the W-190 was businesslike and functional, the Corsair was imposing. The numbers told the story. Empty weight, approximately 7,000 pounds, nearly 2,000 pounds heavier than a Bf-109G. With full fuel and ammunition, the Corsair topped 14,000 pounds, making it one of the heaviest single-engine fighters in operational service. But that weight wasn't accidental or wasteful. As engineers walked around the fighter that first day at Rechlin, measuring dimensions and examining construction details, they began to understand where all that mass had gone. The fuselage was thick, built around a massive Pratt & Whitney R2800 double wasp radial engine that produced 2,000 horsepower at takeoff. For comparison, the Daimler-Benz DB605 engine in the latest Bf-109G produced about 1,500 horsepower. The Americans had built their fighter around an engine that generated a third more power than Germany's best production fighter engine. The engine installation itself demonstrated engineering sophistication that impressed the Rechlin team. The R2800 was an 18-cylinder two-row radial, a configuration that German engineers knew created significant challenges in cooling and cowling design. American engineers had solved these problems with an elaborate system of cowl flaps, baffles, and ducting that managed airflow with remarkable efficiency. The engine could run at full military power for extended periods without overheating, something that German radial engine installations still struggled to achieve consistently. Then there was the propeller, 13 feet 4 inches in diameter, a Hamilton standard 3-blade constant-speed unit that could absorb and translate all 2,000 horsepower into thrust. The propeller was so large that it had necessitated one of the Corsair's most distinctive features, those inverted gull wings that German intelligence had made the aircraft easy to identify from a distance. But the engineers at Rechlin immediately understood the aerodynamic logic. The bent wings allowed the massive propeller adequate ground clearance, while keeping the main landing gear reasonably short and structurally efficient. It was an elegant solution to a difficult engineering problem, the kind of design innovation that only became possible when you had the industrial capacity to manufacture complex wing structures reliably in quantity. The wings themselves were extraordinary, thick, strong, built to handle the stress of carrier operations where aircraft slammed onto pitching decks at high vertical speeds. The main wing spars were heavy forged components that ran the full span, nothing like the weight-optimized structures in German fighters. Each wing contained 3 Browning 50 caliber machine guns with ammunition boxes holding 400 rounds per gun. That was 2,400 total rounds of 50 caliber ammunition, more than most German fighters carried for all their weapons combined. German engineers noted the self-sealing fuel tanks built into the wings and fuselage, protected by layers of rubber and synthetic materials that would swell when punctured by bullets or shell fragments, automatically sealing holes that would leave a German fighter streaming fuel. They examined the armor plate behind the pilot's seat, thick enough to stop rifle-caliber rounds from astern, and the armored glass windscreen that could deflect small arms fire. They studied the hydraulic systems, the electrical systems, the radio equipment, all of it built to military specifications that prioritized reliability and maintainability over absolute weight minimization. What was emerging from this examination was a picture of an aircraft designed according to principles fundamentally different from German fighter development doctrine. The Corsair wasn't trying to be the lightest possible airframe wrapped around a powerful engine. It was trying to be a weapons system that could operate in combat conditions, absorb battle damage, protect its pilot, and remain effective throughout extended deployments. Every design decision reflected that priority, even when it meant accepting weight penalties that would have been unthinkable in German fighter design. The construction techniques were equally revealing. American manufacturing methods emphasized simplicity and speed of production. Wherever possible, components were designed for easy installation and replacement. Panels were held by standard fasteners rather than custom fittings. Access panels were logically positioned for maintenance. The entire engine cowling could be removed in less than an hour by a ground crew using basic tools. For an industrial economy, this made perfect sense. But for German aviation, struggling with increasingly severe material shortages and skilled labor constraints, it was almost incomprehensible. How did you build a fighter this robust, this capable, and still make it simple enough for relatively inexperienced mechanics to maintain in field conditions? The answer, German engineers were beginning to realize, lay not in superior technology or advanced materials. American metallurgy wasn't better than German metallurgy. American aerodynamics wasn't more sophisticated. What was different was the industrial philosophy behind the design. The Corsair was engineered for mass production by a country with effectively unlimited industrial capacity. It was designed to be built in vast numbers by workers who weren't necessarily skilled craftsmen. It was optimized for an attritional war where you could replace losses faster than the enemy could inflict them, where pilot survival mattered more than maximum performance, where operational readiness rates determined effectiveness more than theoretical capabilities. By September 1944, as Rechlin's mechanics continued working to make the captured Corsair flyable, the engineers compiling their technical reports faced an uncomfortable truth. They were looking at an aircraft that represented not just different engineering choices, but a different kind of war. A war where industrial might trumped tactical brilliance, where sustainable production overwhelmed qualitative superiority, where the ability to absorb losses and keep fighting mattered more than individual aircraft performance. And Germany was losing that war. The detailed examination of the Corsair's internal systems only reinforced these conclusions. The fuel system was elaborate, designed with redundancy that seemed almost wasteful by German standards. Multiple fuel tanks, cross-feed valves, boost pumps, all interconnected so that battle damage to one part of the system wouldn't necessarily ground the aircraft. German fighters used simpler fuel systems that saved weight but left them vulnerable to single-point failures. A bullet through the wrong fuel line could end a sortie. The Corsairs system was designed assuming the aircraft would take damage and needed to keep flying anyway. The hydraulic system that operated the landing gear, flaps, and dive brakes used high-pressure lines and actuators built to tolerances that required specialized manufacturing equipment. German engineers noted this with particular interest because the Luftwaffe had struggled with hydraulic system reliability throughout the war. Hydraulic failures had caused countless landing gear malfunctions, combat losses, training accidents. The American system in the Corsair was more complex but more reliable, built with precision components that could withstand the vibration, heat, and stress of carrier operations. The engine management systems revealed another layer of American engineering sophistication. The R-2800 used a sophisticated mixture control and supercharger system that optimized performance across a wide altitude band. Automatic controls adjusted fuel mixture and boost pressure based on altitude and throttle position, reducing pilot workload and preventing engine damage from incorrect manual settings. German fighters required constant pilot attention to engine management, adjusting mixture, propeller pitch, and supercharger settings throughout flight. The Corsair automated much of this, allowing the pilot to focus on combat rather than constantly monitoring engine instruments. The electrical system was equally impressive. The Corsair used a 24-volt system with multiple generators and backup batteries, providing ample power for radios, navigation equipment, gun chargers, and other systems. German fighters used simpler 12-volt systems that were lighter but often struggled to power all the equipment being added to late-war aircraft. Radar warning receivers, additional radios, improved gun sights, all of these upgrades strained German electrical systems that hadn't been designed with significant expansion in mind. The American approach built in excess capacity from the beginning, accepting the weight penalty in exchange for system flexibility. Perhaps most telling was the radio equipment. The Corsair carried multiple radio sets, VHF and HF transceivers that provided reliable long-range communication even under combat conditions. German fighter radios had been notoriously unreliable throughout the war, plagued by interference, limited range, and complex maintenance requirements. Luftwaffe pilots regularly complained about radios failing at critical moments, leaving formations unable to coordinate effectively. The American radio installation in the Corsair was heavier and more power-hungry, but it worked consistently. In combat, reliability mattered more than theoretical specifications. The armament installation demonstrated the same philosophy. 6 50-caliber Browning M2 machine guns, 3 in each wing, mounted outboard of the propeller arc so they didn't require synchronization gear. Each gun was individually mounted on shock-absorbing rails that reduced recoil stress on the wing structure. Ammunition feeds were carefully designed to prevent jams even during violent maneuvers. Spent cartridge and link ejection chutes routed debris safely away from the aircraft. The entire installation was built assuming guns would be fired in long bursts during high-G combat maneuvers, and every component was engineered to function reliably under those conditions. German engineers calculated the firepower these 6 guns could deliver. At the 400 rounds per gun mentioned in the initial examination, the Corsair carried over 200 pounds of ammunition. Sustained fire time was approximately 30 seconds if all 6 guns were fired continuously. For comparison, a Bf 109 G6, with its single 30mm cannon and 2 13mm machine guns, carried enough ammunition for about 20 seconds of combined fire. The FOFW 190A8, with its 4 20mm cannons and 2 13mm guns, had roughly the same endurance. The Corsair's 6 50 calibers, while individually less powerful than German cannons, could saturate a target area with devastating effect. Test data from American sources, captured in various intelligence documents, showed that 50 caliber rounds could penetrate the armor on most German fighters at ranges up to 500 yards. Against lightly constructed Japanese aircraft, the effect was catastrophic. Against the more robust German fighters, multiple hits were often required, but the Corsair carried enough ammunition to achieve multiple hits reliably, and the psychological effect of facing that volume of fire couldn't be quantified in technical reports. Luftwaffe pilots described the experience of being targeted by American heavy fighters as a wall of tracers that seemed impossible to evade. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. By October 1944, the restoration work on the captured Corsair was progressing slowly. Specialized parts were difficult to source. American fasteners used different thread standards than German equivalents. Hydraulic fittings required adapters that had to be custom machined. The constant Allied bombing of German industrial facilities meant that even basic machine shop work faced delays. But the technical documentation effort continued. Engineers compiled detailed drawings of every major component. Metallurgists analyzed samples of American aluminum alloys, noting composition differences that affected strength and fatigue resistance. Aerodynamicists measured wing profiles and control surface geometries, feeding data into calculations that would compare the Corsair's theoretical performance against German fighters. What they were discovering went beyond individual components or systems. The Corsair represented a completely integrated design where every element supported every other element. The robust structure allowed more powerful armament without excessive weight growth. The powerful engine enabled the heavy structure and armament to achieve high performance anyway. The emphasis on pilot protection and system redundancy meant aircraft returned from combat missions that would have destroyed lighter German fighters, preserving experienced pilots who became progressively more effective. It was a self-reinforcing design philosophy that only worked if you had the industrial capacity to support it. And by late 1944, that was exactly what Germany lacked. Then came the dive tests. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. And this is where the German understanding of the Corsair's capabilities underwent its most dramatic revision. By late 1944, Rechlin had developed sophisticated procedures for testing captured Allied aircraft. Test pilots flew the fighters through standardized maneuvers, measuring performance characteristics under controlled conditions. Speed runs at various altitudes, climb rate measurements, turn performance evaluations, and critically, dive tests that pushed aircraft to their structural and aerodynamic limits. The Corsair's dive performance had been mentioned in intelligence reports, but those reports couldn't convey the reality of what German test pilots experienced when they pushed the fighter into a steep dive from high altitude. The initial test runs were cautious, gradually increasing dive angles and speeds while monitoring structural loads and control responsiveness. What emerged from these tests was something German engineers found difficult to believe. The Corsair could exceed 700 km per hour in a dive, 435 miles per hour, and it remained controllable. The control surfaces didn't flutter or lock up. The airframe didn't show signs of structural stress. The aircraft didn't exhibit the compressibility effects that plagued many fighters approaching their maximum dive speeds, where airflow over the wings and control surfaces began behaving unpredictably as local air speeds approached the speed of sound. For German pilots, used to the Bf 109 and W 190, this was a revelation. The Messerschmitt could achieve high dive speeds, perhaps 650 to 700 km per hour indicated airspeed under ideal conditions, but pilots had to be extraordinarily careful. At high speeds, the control forces became very heavy. The rudder became less effective. Pulling out of a high-speed dive required significant physical strength and careful technique. Excessive G-forces during the pullout could cause structural failure. Several test pilots at Rechlin had experienced control surface damage or wing failures when pushing German fighters to their dive limits. The Focke-Wulf handled dives somewhat better than the Messerschmitt, but it too had limitations. Above about 600 km per hour, the controls became sluggish. The aircraft wanted to pitch forward, requiring constant trim adjustments, and the thick radial engine installation created significant drag at high speeds, limiting terminal velocity compared to fighters with inline engines. The Corsair suffered none of these limitations to the same degree. The test pilots reported that even at 700 km per hour, the controls remained responsive. Ailerons were heavy but functional. The elevator required more force but still provided precise pitch control. The aircraft tracked straight without the wandering tendencies that made high-speed flight in German fighters so challenging, and the structural margins were sufficient that pilots felt confident pushing the aircraft to these speeds without fear of catastrophic failure. The engineering team analysed why the Corsair performed so well in high-speed dives. The answer lay in that robust construction they'd been documenting for months. The heavy wing spars and thick skin provided torsional rigidity that prevented wing twist under high aerodynamic loads. The control surfaces were mass-balanced and aerodynamically designed to minimize flutter. The entire airframe was built with safety factors that allowed it to handle stresses well beyond normal combat maneuvering, but there was more to it than just strong construction. The Corsair's aerodynamics were carefully refined to minimize compressibility effects. The wing section was designed to maintain attached flow to higher speeds than German wing profiles. The control surface shapes and actuation systems were optimized for high-speed flight. American designers had clearly anticipated that the fighter would operate routinely at speeds approaching its structural limits, and they'd engineered accordingly. The tactical implications were sobering. In combat, the ability to dive at 700 km per hour meant the Corsair pilot could dictate engagement terms against German fighters. If a Bf-109 or 4-190 got on a Corsair's tail, the American pilot could simply push the nose down and accelerate away. The German pilot could follow into the dive initially, but as speeds built towards 700 km per hour, the German fighter would reach its handling limits while the Corsair still had control authority in reserve. The German pilot would be forced to pull out early or risk losing control. The Corsair could extend away, gain separation, then reverse the engagement from a position of advantage. This wasn't theoretical. American tactical manuals for the Corsair explicitly described these boom and zoom tactics. Maintain altitude advantage. Dive on the target at high speed. Make a firing pass. If the attack succeeded, climb away using excess energy. If it failed, extend in a high-speed dive, then use superior climb rate to regain altitude for another attempt. Never turn with more maneuverable opponents like the Japanese Zero or German Bf-109. Always fight vertically, using speed and power to control the engagement. The Rechlin analysis confirmed that these tactics would be devastatingly effective. A well-flown Corsair could engage German fighters repeatedly, attacking when it held advantage and disengaging whenever the tactical situation became unfavorable. The German fighters lacked the performance to force an engagement. They couldn't catch the Corsair in a dive. They couldn't climb with it. They couldn't sustain high-speed pursuit without risking control problems or structural failure. They were, in effect, fighting on the Corsair pilot's terms. This represented a fundamental shift in the balance of air combat, one that German tactical doctrine hadn't fully confronted. The Luftwaffe had always emphasized pilot skill and aircraft maneuverability. German fighter tactics assumed that superior training and combat experience could overcome material disadvantages. Ace pilots in inferior aircraft could still dominate through better tactics, better positioning, better gunnery. But what happened when the material disadvantage became so pronounced that skill couldn't compensate? What happened when the enemy aircraft was faster, stronger, better armed, and capable of simply refusing engagement whenever conditions weren't favorable? The strategic analysis section of the Rechlin report, completed in December 1944, addressed these questions with clinical honesty. The document noted that the Corsair represented current American production, not experimental or limited deployment aircraft. Intelligence estimates suggested the United States was producing the type in quantities exceeding 1,000 per year, with total production already surpassing 10,000 aircraft by mid-1944. These fighters were equipping both U.S. Navy and Marine Corps squadrons and were being delivered to Royal Navy carriers under Lend-Lease. German fighter production in 1944, despite desperate efforts to increase output, barely exceeded 3,000 aircraft per month across all types. And those production numbers were achieved only by sacrificing quality control and training programs. Newly manufactured aircraft often had defects that required extensive field repairs before they were combat-ready. Pilot training had been cut to minimal levels, with new replacement pilots arriving at frontline units with barely 100 hours total flight time. Meanwhile, American pilots received over 300 hours of training before entering combat, including advanced gunnery instruction and tactical flight training. The industrial disparity wasn't news to German planners by late 1944, but the captured Corsair provided concrete data that quantified the gap. The Americans could build a fighter weighing 14,000 pounds combat-loaded, with 6 heavy machine guns, robust armor protection, and sophisticated systems, and produce it reliably in quantity. Germany was struggling to maintain production of the lighter, simpler Bf 109 while dealing with constant material shortages, labor problems, and Allied bombing of manufacturing facilities. More concerning was what the Corsair revealed about American aviation development capacity. The fighter had been designed in 1938, first flown in 1940, and entered combat service in 1943. By 1944 standards, it was already a mature design, yet it remained competitive with or superior to the latest German fighters that were just entering service. Intelligence reports mentioned newer American fighters in development or early production, improved Corsair models with more powerful engines, the Grumman F-6F Hellcat, which had achieved even more impressive kill ratios than the Corsair in the Pacific, and early jet fighters that would render piston engine designs obsolete within years. German jet development had reached production with the Messerschmitt Me 262, a revolutionary fighter with performance far exceeding any piston engine aircraft, but production numbers remained minimal. Fewer than 1,000 Me 262 seconds would enter service before the war ended, and pilot training problems, fuel shortages, and Allied air superiority over German airfields limited their effectiveness. The Americans and British were also developing jets, and their industrial capacity meant that once those designs reached production, they would quickly appear in overwhelming numbers. The Rechlin engineers compiled comparison charts that starkly illustrated the problem. Engine power. The R2800 produced 2,000 horsepower using fuel that America had in abundance. The DB605 produced 1,500 horsepower using fuel that Germany was running out of. Armament. The Corsair carried 2,400 rounds of ammunition. The Bf 109G carried about 250 rounds total for all weapons. Operational readiness. American squadrons maintained 60 to 70% aircraft availability. German units considered themselves fortunate to field 40% of their nominal strength at any given time. Behind every statistic was a material reality that couldn't be changed through better tactics or pilot skill. American aluminum came from mines in multiple continents, transported on shipping routes the U.S. Navy controlled absolutely. German aluminum came from increasingly scarce sources, vulnerable to bombing raids and partisan attacks. American aviation fuel was refined, from Texas and California oil fields producing millions of barrels per month. German synthetic fuel plants were being systematically destroyed by Allied bombers, and the fuel that remained was of declining quality. American electronics manufacturing drew on a vast industrial base with deep expertise in mass production. German electronics relied on skilled craftsmen, hand-assembling components in facilities that faced constant material shortages and power interruptions. The Corsair's presence at Rechlin, undergoing detailed examination while German engineers documented its superiority in nearly every measurable category, became a symbol of Germany's strategic situation. Understanding the enemy's advantages didn't help if you couldn't counter them. Having detailed technical data on American engineering didn't matter if you lacked the industrial capacity to implement similar solutions. Recognizing that enemy fighters were faster, stronger, and produced in greater numbers couldn't change those facts. It just made defeat easier to quantify. By January 1945, work on the captured Corsair had effectively stopped. Allied bombing had forced Rechlin to relocate much of its testing activity to satellite airfields. The Me 262 program consumed whatever resources remained available for flight testing. Conventional fighter development had become largely irrelevant anyway. If Germany couldn't build and deploy jets in sufficient numbers before being overrun by Allied armies, then no piston engine fighter improvements would matter. The Corsair sat in a hangar, its examination complete, its lessons documented in reports that increasingly few people had time to read. The technical reports remained, however. Detailed drawings, performance measurements, metallurgical analyses, engineering assessments, all carefully catalogued and preserved, even as the Third Reich collapsed around them. These documents told a story that went beyond this single captured aircraft. They revealed an industrial and technological competition that Germany had lost not because of inferior engineering or inadequate pilot training, but because of fundamental economic and material disparities that tactical or technical brilliance couldn't overcome. When American forces captured Rechlin in May 1945, they discovered dozens of German aircraft, captured Allied fighters, and extensive documentation archives. Among the captured enemy aircraft records, they found the Corsair technical reports. American intelligence officers found it surreal, reading German analyses of their own fighter, seeing American engineering decisions explained in German technical terminology. The assessments were professional, thorough, remarkably objective. German engineers had recognized superior solutions when they encountered them and documented those observations honestly, even when the conclusions were uncomfortable. The fate of the Corsair itself remains uncertain. Most sources indicate it never achieved flight status at Rechlin before testing activities ceased. Whether it was destroyed during Allied bombing raids, captured intact by advancing American or Soviet forces, or simply scrapped for salvage materials, isn't definitively documented. What survived were the technical reports, preserved in archives that detailed exactly what German engineers had learned from examining this representative sample of American aviation engineering. The lessons extended beyond the specific case of the Corsair. The fighter exemplified an approach to aviation development that prioritized different values than German design philosophy. Survivability over minimum weight, maintainability over complexity. Operational readiness over theoretical maximum performance, pilot protection over pure speed. These weren't better or worse choices in an abstract sense. They were appropriate choices for an industrial economy, fighting an attritional war where material resources and production capacity determined outcomes more than individual aircraft capabilities or pilot skill. The Corsair's combat record validated this approach completely. In Pacific theater operations from 1943 through 1945, Marine and Navy Corsair squadrons achieved an 11-to-1 kill ratio. For every Corsair lost in air combat, pilots shot down 11 enemy aircraft. This staggering success rate wasn't solely due to aircraft performance. American pilots had superior training. They operated with radar-directed intercepts, good radio communication, and numerical superiority. But the aircraft itself provided capabilities that made that success possible. Speed to engage or disengage at will, firepower to destroy targets reliably, durability to survive battle damage and return to base, protection to keep pilots alive when things went wrong. German fighters, even flown by experienced pilots, struggled to counter these advantages. The tactical manual captured with the Corsair outlined exactly how American pilots would exploit their performance superiority. German tactical doctrine had no effective counter because the counter required matching or exceeding American performance, and German industry couldn't provide aircraft with that performance in the quantities needed. The strategic problem reduced to simple arithmetic. America could build 10 Corsairs for every Bf-109 Germany produced. American pilots received 3 times the training German pilots got. American aircraft incorporated protection and redundancy that German designs sacrificed for weight savings. The outcome was mathematically predetermined. The dive speed revelation, that 700 km/h capability that German test pilots confirmed at Rechlin, crystallized this disparity. It wasn't just that the Corsair could dive faster than German fighters. It was that American engineers had designed the aircraft anticipating these speeds, engineering the structure and controls to handle them. Routinely, accepting the weight and complexity penalties, confident that their industrial system could produce such sophisticated aircraft in quantity. That confidence was justified. The production data proved it. The combat results validated it. The examination of a single captured fighter revealed an industrial and technical capacity that Germany, by late 1944, had no hope of matching. The Rechlin technical reports sit in archives today, hundreds of pages of careful German engineering analysis, documenting American aviation capabilities in meticulous detail. Historians studying the air war find them valuable because they represent a neutral technical assessment, uncolored by propaganda or institutional bias. German engineers at Rechlin had no reason to exaggerate American capabilities or minimize German aircraft deficiencies. They were writing for other engineers and military planners who needed accurate information. The conclusions in those reports are therefore revealing precisely because they're stated so matter-of-factly. The Corsair was faster, it was stronger, it was more heavily armed, it could operate effectively under conditions that would ground German fighters. It incorporated engineering solutions that German industry couldn't replicate with available resources, and it represented production standards that American factories sustained while simultaneously building thousands of bombers, transport aircraft, and other military equipment. These weren't opinions or propaganda claims. They were measurable facts documented through systematic examination and testing. Perhaps the most telling detail in the entire captured Corsair episode was this: German engineers could explain exactly why they were losing the air war. They understood the material and industrial disadvantages. They recognized the technical superiority of Allied aircraft. They could quantify the production disparities and training deficiencies. Understanding the problem in exhaustive detail didn't provide solutions. Some problems, once fully understood, reveal themselves to be unsolvable with available resources. Germany faced exactly that situation in the air war by 1945. More knowledge just made the inevitable outcome clearer. The captured Corsair at Rechlin taught German engineers that lesson more thoroughly than any battle report could. Here was an enemy fighter they could examine component by component, system by system, measuring and analyzing every design decision, understanding the engineering philosophy behind each choice, and having completed that examination, having documented every detail, they faced the reality that they couldn't build anything comparable. Not because they lacked engineering talent or technical knowledge, because they lacked the industrial capacity, the material resources, the fuel, the aluminum, the specialized manufacturing equipment, the trained workforce, all the infrastructure that made American production possible. That was the ultimate revelation. The dive speed was impressive, 700 kilometers per hour in controlled flight, beyond what German fighters could match. But more impressive was the entire industrial system that could design such an aircraft, engineer it for quantity production, build it by the thousands, train pilots to fly it effectively, deploy it to combat units worldwide, and maintain it under combat conditions. The Corsair wasn't just a faster fighter. It was a product of an economic and industrial system that Germany was fundamentally losing to. When the last Rechlin technical report on the captured Corsair was filed away in January 1945, it marked the end of any realistic hope that Germany could achieve technological parity with Allied aviation. The jet fighters under development offered theoretical advantages, but production realities meant those advantages would never be deployed in sufficient numbers. The war would be decided by the clash of industrial systems, and Germany's industrial system was being systematically dismantled by Allied strategic bombing, while America's expanded continuously, untouched by enemy action. The fighter that sat in the Rechlin hangar, captured by chance in a Norwegian field in July 1944, had become a silent witness to Germany's defeat in the air. Every rivet, every structural component, every system installation told the same story. This was what you could build when you had industrial might, material abundance, and engineering confidence. This was what you could achieve when you designed for production, maintainability, and operational effectiveness, rather than minimum weight and theoretical maximum performance. This was what fighting an attritional war against an industrial superpower looked like when you were on the losing side. The Corsair's lessons remained relevant long after the war ended. Aviation engineers studying the aircraft in museums today still find insights in its design. The inverted gull wing remains one of the most recognizable profiles in aviation history. The robust construction influenced post-war fighter development. The emphasis on pilot protection became standard in military aircraft design worldwide. The approach of accepting weight penalties to achieve operational advantages, rather than optimizing for theoretical performance metrics, influenced how air forces evaluated fighter requirements for decades. But perhaps the most enduring lesson is the one German engineers learned at Rechlin in late 1944. Understanding your enemy's capabilities doesn't ensure victory. Having detailed technical knowledge doesn't overcome industrial disparities. Recognizing superior engineering solutions doesn't help if you can't implement them. Sometimes, the most sophisticated analysis just makes defeat more comprehensible. The captured Corsair, examined with scientific precision by skilled engineers, taught that lesson with brutal clarity. In war, understanding exactly why you're losing is sometimes the cruelest knowledge of all, because it forces you to watch defeat approaching with perfect clarity and no ability to prevent it. That 700 km/h dive speed German test pilots achieved in the captured Corsair wasn't just a performance figure. It was a measurement of the distance between two industrial systems, two approaches to aviation development, two philosophies of modern warfare. And by late 1944, that distance had become unbridgeable. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.